Welcome to part 3 of our lesson on nuclear chemistry. This lesson, I would be discussing about the energy of nuclear reactions. So we're going to calculate the mass efficiency and the nuclear binding energy. So this is the energy that is released during nuclear reactions. Start. So let's start our discussion now. How much energy there is in radioactive decay? So radioactive decay generally gives off large amounts of energy, more than that we calculate in thermochemistry. So where does it come from? So the answer lies in something called mass defect. So in mass defect, that's the difference in the mass of the nucleus versus the mass of the particles that are present in it. So let's discuss first the law of conservation of mass. As applied to chemical reaction, the law of conservation of mass states that mass is neither created nor destroyed in transformation of matter. So that also applies to nuclear reactions and not only for chemical reactions. So there is that the law of conservation of energy as well, and this is what we studied in thermochemistry, that energy cannot be created nor destroyed. And then in nuclear reactions, there is that law of conservation of mass and energy. It states that mass can be converted into energy and energy can be converted into mass. So that's the law of conservation of mass and energy. So let us again consider the masses of the different particles in an atom. And again, you can see that the electrons have very, very small masses. The protons have slightly lower masses than the neutron. So the most massive particle is the neutron. And since these are the two heaviest particles, they reside inside the nucleus. So the nucleus carries the mass of the entire atom. Okay. So the mass defect, as I said, is the difference in the mass of the total mass of the individual nucleons versus the mass of the nucleus. So for example, carbon-12 has a mass that is equal to 12 atomic mass units. That's the mass of 12 nucleons. So that would be the 6 protons and the 6 neutrons. So if the mass of the entire nucleus is considered, it is equal to 12 atomic mass units. They have a way of finding that out. So do not question scientists. They have a way of finding out the mass of the entire nucleus. Okay. So for each nucleon, it has a mass that is greater than 1.0073 for the proton, 1.0085 for the neutron. So if we consider the mass of all the particles inside the nucleus and compare that with the 12 atomic mass unit mass of the entire nucleus, there is a slightly less difference in the mass of the entire nucleus as compared to the mass of the nucleons. So the missing mass is called the mass defect. So the mass defect, delta M, is equal to the mass of the nucleons minus the mass of the nucleus. We'll have a sample problem about that later. Let's go to the derivation of the formulas first. So binding energy is a measure of the force holding a nucleus together. So that binding energy is said to be equal to the change in energy during the nucleus formation. So when the protons all having similar charges and the neutrons having zero charges are starting to form the nucleus of an isotope, so a certain amount of energy is necessary to hold them together to counteract the repulsive forces of the protons. So that energy is called the binding energy of the nucleus. So the binding energy is also the energy needed to separate the component nucleons. So enough energy to hold the nucleons together to prevent the protons from repelling each other. And that's the same amount of energy that is needed to break them apart. Okay? So does that binding energy come from? So let's consider Einstein's special relativity equation, E is equal to mc squared. So the binding energy is equal to the change in energy during nucleus formation. So it is equal to delta M, a particular mass inside the atom, multiplied by the square of the speed of light. So this is how we determine, or this is how the binding energy is calculated. So C is the speed of light, and it has a value equal to 3 times 10 to the 8 meters per second. So in our example about the mass defect for carbon, so let's consider that example here. So for carbon-12 isotope, the mass of carbon-12 is 12 grams per mole. So let us consider 1 mole of carbon-12 isotope. So the mass of that is equal to 12 grams for 1 mole. So the mass of the neutron is 1.00867, while the mass of the proton, a single proton, is 1.00783. Okay? So if there are 6 protons and 6 neutrons in an atom, the total masses of the nucleons can be calculated. So 6 times the mass of the neutron, 6 times the mass of the proton, and total that, it's equal to 12.099 grams per mole. Considering the mass of 1 mole of carbon nucleus, that is equal to 12 grams, so there is a slight difference. Although it is very slight, it is very significant. So 12.00999 minus 12.00 is equal to 0.099, and that is the change in mass, or this is the mass defect. Now let's calculate the binding energy. So using the formula E is equal to mc squared. So the mass is equal to 9.9 times 10 to the minus 5 kilogram per mole. Look at this. It has to be converted into kilogram because 1 joule of energy is equivalent to 1 kilogram per meter square. Square of the velocity is meter square per second square. So the mass has to be converted into kilograms. So the speed of light has a unit of meter per second square. So mass times the square of the speed of light will give us a value that is equal to 8.91 times 10 to the minus 12 joule per mole. So this is a very huge number. Let's convert the unit of energy into kilojoules. So it becomes 8.91 times 10 to the 9 kilojoules per mole. So since carbon-12 has 12 nucleons, the binding energy for each nucleon can be obtained by dividing the binding energy that we have calculated here by 12. So this is the energy, binding energy per nucleon of carbon. So that is how binding energy is calculated. So that's the end of our discussion on this topic. Let's now proceed to the next lesson.